Hello everyone, my name is Megha and I'm a third semester master's student at San Francisco State University. Today I will be talking about the robotics project that I had for fall 2020 semester for Engineering 869, and the project was done under the guidance of our professor, Dr. Azadi. So initially, I'll go ahead and talk about the robotics course that we had and what all we did. So it was mainly focused on the introduction of the robotics, on understanding the concepts of robot manipulators in terms of deriving forward and reverse kinematics and motion planning, as well as hardware performance of motors and actuators. Robot dynamics and modeling was also devised to design controllers for target motion, traffic tracking of manipulator, application of robots in automation, medicine, and service field was also covered. And at the same time, we had the great opportunity of working into details with MATLAB, Simulink, and Robotics Toolbox and Simulink to work on this project. We had all these experiences. Here, the project is going to be about SCARA robot. So SCARA robots is a typical industrial robot. The acronym itself stands for Selective Compliance Assembly Robot Arm. By the virtue of SCARA's parallel axis joint layout, the arm is slightly compliant in XY direction, but rigid in Z direction. Hence the term selective compliance. This is advantageous for many types of assembly operations. For example, inserting a round pin in a round hole with binding. And the features allow the arm to extend into confined areas and then retract or fold up out of the way. This is advantageous for transferring parts from one cell to another for loading and unloading process stations that are enclosed. SCARA is generally faster compared to the Cartesian robots. It was initially developed under the guidance of Professor Hiroshi Makino. It was a new concept back then in 1981. Well, as we all know, this car robot is mainly used for pick and place and assembly operations where high speed and accuracy is required. So there are a few strengths as well as a few limitations that we see in the SCARA robots nowadays. The strengths mostly are speed, precision, and the compactness that is provided by these robots. But it also includes a few limitations like small range of motions, small payload capacity, and selective compliance. Further, we see that there are, irrespective of all the limitations that I mentioned here, there are many industries which are using SCAR robots right now. Those industries are like electronics, telecommunication, food and beverages. The picture you see on the right is from the food industry. Then we have retail manufacturing. Then we have the pharmaceutical one here and the automotive one here. And these are a few industries which are currently making use of SCARA robots and utilizing all of their speed and compactness, and all these high volume producers are using those features. So the overall goal of this project is to create the SCAR robot and to utilize the features of MATLAB Landscape and robotic system toolbox of Simulink, and see how we can create a robot and change its parameters and to make sure that the arms are moving in a specific uh, direction on a specific motion, they're following a specific trajectory, and we are able to put up all the limitations that we want. So these are the basic goals that we are going to cover in this project. Here are some of the basic details about the model. So the output of this model, the Simulink output of this car robot is going to look something like this. We're going to have one base body, and this is going to be link 1, link 2, and this is going to be a vertical link 3. We are going to use 2 revolute joints here, and then we are going to utilize one prismatic one here, and there's going to be the end factor. We are going to define the waypoints, basically defining the motion that we want the end factor to have. We'll be utilizing trapezoidal velocity profile trajectory. I'll be talking in detail as we go ahead in this presentation. So initially, before moving forward, let's talk about the softwares that we're using. So We'll be using Simulink, which is a MATLAB-based graphical programming environment, and mainly used for modeling, simulating, analyzing multi-domain dynamical systems. Its primary interface is graphical block diagramming tool and a customizable set of block libraries. It can either derive MATLAB or be scripted from it. Like we can create a script in MATLAB and use that to drive the robot or whatever graphical block diagram we're using. We'll be using that part as well in this project. And it's widely used in automatic control and digital signal program. So these are some of the basic details about Simscape and robotic system toolbox. Like it enables to rapidly create models, and we'll be using robotic system toolbox, which provides tools and algorithm for designing, simulating, and we'll be utilizing all these, the ones mentioned here, like forward and inverse kinematics, trajectory generation, etc. So this is what the Outlook is going to look like. I'm going to show you the one which we're using after I had created the blocks for this particular project. So here is the Simulink model for this. We have clock, we have trapezoidal velocity profile trajectory, inverse kinematics block, then we have the robot block, which includes all the different parts, which I mentioned earlier, mux and demux, and we have forward kinematics block and the scope. So let me just go ahead and show you it onto the MATLAB. So let's go here. And this is where I have created the block diagram. So if you go into this trapezoidal velocity profile trajectory, you can see that we have mentioned waypoints. So let me just do this thing. Let me go ahead and run this. Here I have, as you see, I mentioned the waypoints. So I'm going to go ahead and run. And once this is done running, I'm going to show you that we go ahead and we have this rigid body transform, that rigid body gets created here. And if you go ahead and click on this, you will see that it defines all the base and bodies which are included in this particular robot. So it has got one base, and as you see, it's got like 3 other bodies. So yeah, let me just run it for the 3 joints. And if I go ahead here, there you go. I'm going to just run it. So the previous one was for 2 joints, and this is for 3 joints. If you go ahead and see here, like we have 4 bodies here. So we're going to have 3 link bodies and 1 infector, and we have 1 base as well. So we'll go ahead and run the trapezoidal one with the 3 joints. Okay, let's go ahead and run this particular simulation. So if you go ahead and here, you see the waypoints, it clearly says that's a base workspace. And if you open it up, you'll see all the values mentioned here. And for the inverse kinematics, we have this rigid body tree here, and this is the conversion where we're converting from translation vector, which is the input, into the output of homogeneous transformation. And here's the robot, like I was mentioning before, we have the base here. This is the base that we're using, which is 0.3 meters high. And then we have link 1, link 2, and link 3. This is the link 3 that we are using, which is 0.2 meters in height. And if we go back, these are the 2 revolute joints that we are using for the initial link 1 and link 2. And this is the prismatic joint, because we want this to move in a particular direction, like on one of the axes. For the revolute joint, what's going to happen, it's going to go ahead and revolve. Like it's for revolution, and this is for linear motion. So if we go back, then we have forward kinematics block here, in which we have again the conversion going on here from homogeneous to translation vector. And this is the scope for seeing the output waveforms that we get. So if I go ahead and run it, I'm going to run it for 5 seconds here. I'm going to go and click run. And if you come in here, this is where it's going to go ahead and run. So here, this is right now the top view, mentioning here the x-axis, the y-axis, and the z-axis. We do have the option of changing the view and go to isometric view. This is exactly how the model looked like into the presentation, which I was showing before. And this is the base. This is link 1 here, link 2. This is link 3, and this is the end factor. Right now, it's going to go ahead and move accordingly. So I ran it for 5. As you see, it's going down. It's going to go ahead and uh, complete the trajectory of the waypoint that we mentioned before. I'm going to go ahead and directly run the animated movie that I created out of this. So we do have option of creating a video here and change the views from here. We can go ahead and look at the top view. It is right now going ahead and completing that trajectory. So let's go ahead and look into the movie that I had created. So I'm gonna go ahead and play. So right now, the one video that I created, this animation one, is from the top view. We have x-axis here and y here and the z going in. So this is what it looks like after creating and going onto the trajectory. So yeah, this was the project that we were looking forward throughout this particular course that we had with Professor Azadi. It was a really amazing project that we worked on. It was very engaging and of course informative for us. It is just one single part of robotics that we have stepped on, and with all the knowledge that we have gained in this course, I'm looking forward to go ahead and explore further into the robotics area. I'm really thankful for Dr. Azadi for guiding me with this project. Thank you so much.